starting Unit 7, which is a unit involving maximum and minimum problems. So today in this video we're going to start with just a quick introduction to the concept of max and min problems. And if you think back to your advanced functions classes, you've used some language around local max and min points and absolute or global max and min points. Okay, and we're just going to talk about that a little bit to get started. Local max min points, you really identified these in advanced functions, but you've been finding them since grade 10. Now that we've learned calculus, we have a calculus way to find these local max min points. If I just think about a curve, okay, so a curve, something like that, this would have one local max and one local min. And if I think about this in the calculus sense, at the local maximum, the slope of the tangent would be 0. At the local minimum, the slope of the tangent would also be 0. So we can find, using calculus, these local max min points by taking the derivative set the derivative equal to 0, and then solving for x. And that would give us the x value at those local points. Talking about absolute max or min, they're slightly different than local. Absolute max and min points represent the highest or lowest point that the function reaches. So let's look at an example. So let's look at this graph that I've drawn here. We'll call this graph number 1. And we're going to fill in this table to the right. And we're going to fill it in by answering these questions. What are the local max points, local min, the extreme values, I'll define that in a second, the absolute max, and then the absolute min. So just from what you know from advanced functions, you should be able to identify any local maximums. So these are the points where the curve looks like the top of a hill, and I can see 2 local maximums. I have one at the point 2 and 4, and I have a second local maximum at the point 4 and 3. For local minimums, these are the parts of the curve that look like the bottom of a valley, and I see one local minimum at the point 3 and 2. And some of you might be saying to yourself, well, I see other points that are lower than this local minimum. Why aren't we identifying them as local minimums? Well, we don't identify them as local minimums because you can see at these 2 endpoints, they don't form that nice trough of a valley. They're just endpoints. In fact, these 2 points, the ends of the graph, would be our extreme values. Okay, we might call those extreme values the So I have one endpoint at the origin at 0 and 0, and I have a second endpoint at 5 and 1. So now we need to identify the absolute max and absolute min, and to do this we're going to look at both our local max and our local min points, as well as the extreme values. So to find my absolute max, I'm going to look at my list of points that I've identified, and I'm going to pick one, and I'll pick the highest point. So I'm looking at the y values, and I'll pick the highest y value. And it looks like my highest y value happens at the point 2 and 4. So that point 2 and 4 is the highest that this curve gets based on my drawing. For the absolute min, I'm going to look at my points, and I'm going to pick the lowest y value. And it looks like my lowest y value is this extreme value at the point 0 and 0. Okay, so we can find local max and local min based on what we know from advanced functions. For extreme values, we're looking at the endpoints. And then for absolute max and absolute min, we want to take a look at all those points, and we want to identify the highest y value and the lowest y value. Okay, let's do a new function. Okay, here's our second function, like slightly different. And now we kind of have to abandon how we would do this in advanced functions and think about the calculus way of doing this. The calculus way of doing this tells us that to find a local max or a local min point, we're looking at, or we're looking for places on the curve where the slope of the tangent is 0. So where our tangent would be flat. And in this particular curve, that happens once. That happens at the point 3 and 3. And here's where calculus needs a little bit of work, and we're going to do a little bit of practice on this. At that point 3 and 3, when we get that slope of 0, we don't know if that is a local max or a local min. So we're going to call it both, local max and local min. For extreme values, our endpoints, well, I have a vertical asymptote at at x equals 5. And I have another vertical asymptote through x equals 0. And you recall that around these vertical asymptotes, functions approach infinity. So even though I identified some local max and local min, my absolute maximum happens when x equals 5 and y approaches positive infinity. Never gets there, but it approaches it. My absolute minimum happens when x is 0 and y approaches negative infinity. Again, we'll never get there, but we'll get close to it. So being able to do this from graphs is well and good, but we need to find a way to do this just from equations. So our method for finding extreme max and min values on some interval between a and b is as follows. We're going to calculate the value of the function at two different places. We're going to calculate the value of f of x at all points on the interval where the derivative of the function is equal to 0. find the derivative, set it equal to 0, solve for x, and then calculate f of x at those points. And we're also going to calculate f of x at the endpoints, the extreme values. So the endpoints are x equals a and x equals b. The absolute maximum will be the largest of these values, and the minimum, the absolute minimum, is the smallest. Of these values. So let's practice that. We want to find the extreme values of the function f of x equals negative 2x cubed plus 9x squared plus 4 on the interval negative 1 to 5. So our first step, based on our method, is to find the derivative, f prime of x. F prime of x is equal to negative 6x squared plus 18x. Now that we've found the derivative, we're going to set it equal to 0 and solve for x. So 0 equals negative 6x squared plus 18x. Let's factor. And we can factor out a negative 6x. So this gives us two values, or two solutions, and x equals 0 and x equals positive 3. My last step is to sub x equals 0, x equals 3, and the endpoints, x equals negative 1 and x equals 5, into f of x. So I'm solving for f of negative 1, f of 0, f of 3, and f of 5. And when I do that, I get values of 15, 4, 31, and negative 21. So I can use this information to determine what the maximum value is and what the minimum value is. Looking at this list, to find the maximum value, I want to pick the largest, and the largest is at the point 3 and 31. And looking at this list, I want to find the minimum, and the minimum happens at 5 and negative 21. And what I would suggest you do is hop online, Wolfram Alpha or Google, and verify by graphing. You don't have to, and we won't be doing that yet, but it just might be good to solidify this with yourself, that this is the maximum value on this interval, and this is the minimum value on this interval. And then one final thing, just a challenge for you to try on your own. If I of t models light intensity and I of t is equal to t squared plus 2t plus 16 over t plus 2. I'd like you to find the minimum intensity of light when t is on the interval 0 to 14. Okay, so see if you can do that, and bring your answer to class tomorrow and we'll compare. In class tomorrow we're going to do further discussion about our method for finding max and min values on the interval between A and B. So we'll do some more work around this, and I'll give you some more time to practice. Thanks for watching.